Welcome to the Wednesday morning session. It's a great pleasure to introduce Rupert Frank from LMU Munich. We'll talk about the Wehrl entropy problem.
Thank you. Good morning. Thanks to Alkera and all the other organizers for putting together this meeting. It's really nice for me, particularly to see many people that I haven't seen in a long time. And I'm going to speak about something that is perhaps not in the center of this meeting, but nevertheless, I hope interesting for some of you. It is, I mean, on the one hand, there has been some, so this problem has been around for 40 plus years, but in the last few years, there has been some extra progress. And on the other hand, there are many open questions that still remain. And it might be, especially for you who have tools and ideas how to treat with entropy kind of problems, that you want to address these questions. And I would be happy if this would lead to some further progress. And the main notion. Where should I go? Okay, good. So the main notion that's behind all this is the notion of coherent states. Okay, so and I mean there are different coherent states in different contexts. Actually, in very many contexts, you arrive at this notion of coherent states. A very simple example is just if you have a basis. Okay, that's the simplest. I mean, an orthonormal basis, that's the simplest example of coherent states. But then there are more complicated ones, and typically it's what's called overcoherent. Okay, so you have many more elements in your family of coherent states than you have basis elements. And usually they come with certain symmetries of the system, and the index of this big family of coherent states has a special meaning that's appropriate to the problem. Okay. Now, this arises, I mean, both in quantum theory. I mean, this goes back really to the very early days of quantum mechanics. It also arises in signal processing, and in many questions where there is something, a relation between something, let me call it classical, and something quantum, and you want to understand the quantum nature of things via this classical. So often these coherent states come with a certain parameter, and if this parameter is large or small or whatever, then you're close to a quantum regime. To a classical regime, sorry. But that's not what's going to interest me today. I want to ask universal in the sense of non-asymptotic questions. Okay, so I have a given set of coherent states, and then I want to ask questions. And now I don't want to make this too complicated, too abstract. I want to look at the simplest family of coherent states there is, and these are the Glauber coherent states that probably most of you have seen. So we are in a quantum system of one continuous variable. The Hilbert space is L through R. Okay, and now the coherent states that parameterize by two real numbers, P and Q, and that should remind you of classical phase space, Q is position and P is the momentum. And the states are simply Gaussians, where Q means where the Gaussian is centered, and P is sort of the typical momentum of this Gaussian. Okay, and then there is this H bar parameter in there, which I said I don't care. I mean, that gives you a relation when you use those in applications and you play with this parameter. But now we just don't care about this parameter. Okay, so these states parameterized by P and Q are the Glauber coherent states, and they satisfy this completeness relation. Okay. So it's a continuum of states, but with those, they are sort of like a basis, except that they're way too many. Okay, this is the relation. That's not hard to prove. It's essentially just Cauchy-Riemann theorem. Good. And now, what we want to do is we take a quantum state rho in this Hilbert space. And what we do is we take expectations in our coherent states. And now it follows immediately from the completeness relation that this gadget, right, this expectation value, that's now a function of P and Q, a function of classical phase space, that this is actually a function that integrates to 1. And then simply because the state is non-negative, this function is non-negative, so what we have is a probability density. So we have associated for one state a probability density in this space. And now what Wehrl suggested is that you look at the continuous entropy of this probability density, right? Just the density, log density integrated over the parameter space. Okay, and he suggested this is what's called the Wehrl entropy of this constant. And when I was preparing this talk, I was wondering how much should I explain about this? How did Wehrl come up with the notion? Why did he suggest this? At the end, I decided to not talk very much about it. You know, this paper of Wehrl, that's from the late 1970s. So people back then cared about different aspects. I mean, this was a time when some of the main properties of quantum entropy were just being proved. And these are things that are now in the textbooks. And people back then were more worried about some things that we don't worry so much anymore. So I think this is nice reading. Have a look at, so there's this paper, the 79 paper, there's a year earlier, so there's a long this review paper by Wehrl where he discusses the notion of entropy. It's nice historical reading, but for this talk, it's not terrible. I mean, one thing, at least that I want to mention is since, you know, just by the Schwarz inequality, this expectation value is always less or equal than 1. Okay, so it's a probability density, but it cannot concentrate too much. And that has the effect that this quality, the x log x function, is always negative, with minus sign is positive. So this entropy is always greater or equal than 0. That's a feature that the quantum entropy has, but that other notions of classical entropy have. And I mean, that was one thing that they liked very much. If you think a little bit harder, then you can actually lower down this Wehrl entropy from below by the von Neumann entropy. But again, I mean, that's mostly historic background. So the point of view that I want to take for this talk is motivated by some desire to understand notions of entropy. Wehrl came up with this notion. I'm not claiming that this has any immediate physical applications. I mean, this is motivated by application in physics. It's sort of, people have crystallized some inequalities, some things they want to do, but from there on, it's more or less a mathematical object. And what I want to tell you is that I think there's a lot of deep mathematics hidden. And if we uncover that, then we would perhaps better understand what coherent states are and why we choose these or others. And I think there are things to be understood in this notion, behind this notion, even if there are no immediate applications. So the question that Wehrl answered when you have this notion of entropy is a very natural one. I mean, which states are those which have minimal entropy? Okay, so once again, you have a state rho on your L2 of R. You have this notion of entropy. Now, how small can this thing be? Which states rho are the minimal entropy states? And Wehrl came up with a conjecture. Wehrl said the minimal entropy states are the coherent states themselves. Okay, so those that you use to define the thing are the minimal ones. And again, what's sort of behind this is about how close you can concentrate in phase space. You cannot concentrate arbitrarily close. And so the coherent states are the ones that are optimally concentrated in phase space. That's roughly speaking what's behind. Okay, so when you take a coherent state, then you can compute this overlap explicitly, and you find that the value is 1 for any coherent state. The whole thing is independent of which coherent states you take. And so Wehrl's conjecture was that this Wehrl entropy is lower bounded by 1, and equality occurs not only if you have a coherent state, but also only if you have a coherent state. Now that Wehrl paper was submitted in 1977, it was published in 1979, and in between, in 1978, Lieb had already proved that conjecture. Okay, so this, what's written here, conjecture, this is actually a theorem. And what's perhaps a little bit surprising is that Lieb, in the proof, used two very, very deep theorems in harmonic analysis. Namely, you might remember there is this Hausdorff-Young inequality about the Fourier transform, right? The Fourier transform maps a L1 function to an L infinity function and is an isometry on L2. But now what do you do with p's in between? And so Hausdorff-Young is something that says what does the Fourier transform with a function LP? And it gives an inequality, and that inequality, usually when people prove it in basic, real analysis course, they prove it with constant 1. But actually the constant is smaller, strictly smaller. And the optimizer for that inequality is a Gaussian. Okay, that's hard to prove. Even, some of these sharp inequalities from the 70s have become easier as years go by, but I don't know any simple proof of this Hausdorff-Young. And there's yet another one, another inequality, this Young's inequality about convolutions. Again, this is still considered a deep inequality in its sharp form. These are two inequalities that have Gaussians, but that's essentially all about these inequalities that is reminiscent of Wehrl entropy, right? I mean, I guess nobody would have thought that the problem of computing minimal entropy states has anything to do with these two inequalities. But anyway, he found that connection and was able to put them together in a rather clever way to prove this conjecture. Yeah. Okay, and then I should mention that some 13 years later, Carland gave an alternative proof of this theorem, and he was now able also to add the only if. So Carland could prove that only equilibrium states achieve equality. And so again, Carland's proof is very ingenious about some special properties of analytic functions, and is perhaps not the proof that you would expect if you think about how natural in some sense this conjecture is. All right, so what did Lieb and Carland actually do? Well, Lieb and Carland actually did not look at this x log x function that appears up there, but they looked at a more general object. And what they looked at is, well, take any function f of this expectation value of the state. By the way, I perhaps just to clarify terminology, this expectation value of rho in state p and q, that comes with many names. People call it the Husimi function, other people call it the Lowe symbol, the short-time Fourier transform. There's something, the Bartman-Seeger transform, FBI transform. These are all essentially the same things. It appears really in very many areas of mathematics, and each community has its own name. So however you call it, you can take not only the x log x function of it, but you can take any concave function and ask the generalized question: if you call this an entropy, this depends on f, the fact that f is concave, has some entropy, it's some entropy-like features, and now you ask, what are the states that make this minimal? And what Carland and Lieb did is actually when you take this f as a power function, then they said, again, optimizers are exactly equivalent states. And what I want to tell you here, that's a new result, or at least part of it is new, namely you take an arbitrary concave function and you minimize it, and optimizers are only the equivalent states. Okay, so this has nothing to do sort of with this x log x nature of the function. This is really a general property of concave functions. I should mention, right, the power case was done originally back by Lieb and Carland. The inequality itself was proved some 9 years ago by Lieb and Soloway. But they got it through a limiting argument. It's actually a quite involved limiting argument going through Bloch coherent states that I'll talk about later. And in this limiting process, they lost the cases of equality. And so the new result is that you get the cases of equality for general concave functions. Perhaps even more important than that is that this proof that I want to tell you about later of this inequality is quite a lot simpler than the ones that that have been there before by But anyway, so this is, some people call this the generalized Wehrl entropy, and what this proves is that states with minimal Wehrl entropy are exactly the coherent states. Now here is, it's sort of a sideline to the story I want to tell you. It's an answer to a stability question. So imagine, so the minimum Wehrl entropy is 1. Now imagine you have a state that gives you Wehrl entropy 1.0001. What can you say about that state? I mean, is this state close to a coherent state, right? Because that would be the guy that gives you value 1. And what this theorem tells you here, it's on the slide, and that's less than a week old, is yes, that's true. So you can bound the distance of the state to a coherent state in trace norm by its difference to the minimal value. Okay, so if you know that this guy, this is the Wehrl entropy, I mean, F could be x log x, but it can also be anything else. If this thing is close to the minimal value, then the state has to be close to that. So almost states of almost minimal Wehrl entropy are almost coherent states. That's what this says. And if you're familiar with this type of inequalities, then you might pay attention to this power 2. This means sort of, as you expect, right, that you vanish quadratic. As you approach the minimum, the function has a non-degenerate minimum there. You know, that happens in most cases, but not always. But it's of course hard because you have a minimum. This function, that's a function in infinite dimensional function space, and that its minimum is quadratic requires. Okay. Now this constant that appears here is explicit in the sense that we do not use any compactness along the way, proving it. But I should say that I don't have a number that I can tell. So I think it's still an interesting question to do that a little bit more quantitative. I mean, you know, we could just follow the proof that we give and also the ingredients that we use. But, you know, if you use a factor of 2 on every page, then after 20 pages, you've lost quite a lot, and that might not render inequality so useful. So that is one of the questions that's still left open. The other question, I don't think this is too hard, but I've stated this for pure states. I think it's valid for mixed states as well. And first, the last remark I want to make is these stability questions, they have really had a lot of interest in mathematical analysis in the past 15 years. A lot of people have looked at, you know, your favorite function and inequality. What can you say if you have almost uniformity? It started mostly with the isochrometric inequality, but then has become a big industry. In particular, there have been quantitative versions of the Hausdorff-Young and the Young inequality that I mentioned before, but those are not enough, at least as far as I can see. Anyway, that was just an aside. Let me get back to the real topic. So the real topic was, we have a family of coherent states, which happen to be Glauber coherent states on the previous slide, but can be other coherent states. We use those to make out of a coherent state a function on classical phase space, and then we were computing classical entropies, and we're looking at minimal entropy states. Okay, now second example. These are the Bloch coherent spin states Now, I think almost everybody has seen those before. This is nothing surprising. Let me just fix my notation. So you have a spin J representation of SU2. Okay, SU2 has three or the algebra of SU2 has three generators. This gives rise to three operators S1, S2, S3 on your representation space, and they satisfy certain conditions. Okay, now what you do is you dot, so omega, that's a unit vector, not three, and you dot that vector into this vector of operators S, and now you look at this operator, and then its highest and its lowest eigenvalues are non-degenerate. And we take this coherent state corresponding to the direction omega as the projection to, say, the lowest eigenvalue of this. Okay, so that is one of the possible definitions of block coherent states. Good. And these guys satisfy a completeness relation, just like we had in the previous slide. So if you integrate these guys over the unit sphere, then you get the identity or consequence. Okay. Now we do the same thing. We take the expectation of a state rho. This is now a state in this finite dimension space, right? In this H, which is C to the 2J plus 1. We take the expectation, we get a function on S2. We compute, say, its classical entropy, x log x, okay? And we ask ourselves, what are the states for which this is minimum? Same question as before. That question was asked by Lieb immediately in 78, immediately after he had solved this Wehrl entropy problem. He formulated this problem and conjectured that the optimizers are again the coherent states themselves. Now, in these intervening almost 40 years, Lieb has given this to many, many postdocs to solve it. It has remained open until 2014, when he, together with Soloway, was able to prove, yes, it is indeed the case. The states of minimal Wehrl entropy, in this sense, are exactly the coherent states. The proof is completely different from the one that we've seen before. There is no Hausdorff-Young inequality, there is no Young inequality, there are no analytic functions, at least not obviously. They came up with a completely different proof. It's a proof that you might be interested in. It's really very much based on certain quantum channels that you understand how you go from spin J to spin J plus 1 and J plus 2 and so on. It's a cute proof. I don't have time to go through it. I just put here a sample result again in this direction, again from last year. Lieb and Soloway, because they did this, you know, that you go from spin J to spin J plus 2, J plus 3, J plus 4, and so on. Again, they did a limiting argument. They lost the cases of equality. This new theorem here gives you the cases of equality. However, what's perhaps a little bit more important here is that this is the same proof as the one for cloud coherent states. So there is one proof that works in both settings, which I mean is at least goes in this direction that there should be something general. So what have we done? I mean, let me summarize the first part of this talk. Okay, so we've seen two examples of coherent states, and we've used those to make out of a quantum state a classical probability distribution. We computed its entropy and we asked about the minimal entropy states. And in both cases, it had turned out that it's the coherent states themselves that have the minimal entropy states. And now when you hear this, obviously you think there must be something general. I mean, that was the belief that Lieb had in 78 when he formulated this conjecture about the coherent spin states. But we're not closer to that. And so that's the big open problem that I want to ask. Somehow, what's the general framework? How can you phrase this? what is really hiding behind that. And I'll give you some thoughts on the next slide on how you can address it. I should say that one of the questions that I do not address in this talk here is, see, when you have this, I mean, I always stated these results about general states rho, but really, since f is a concave function, you can immediately reduce to rank 1 states, to Q states. Okay, that's sort of the first step that you do. There are other questions that are behind there. So for instance, the Palmer had a nice result where he minimized the Wehrl entropy. There, this one. So the original Wehrl entropy, he minimized this under a constraint on the quantum, the von Neumann entropy of rho. So what is the minimal Wehrl entropy if you have a given von Neumann entropy? Turns out that you can solve this problem, and the solution is given by a Gaussian state, that has the right entropy. Okay. Now again, these are this is known in the Glauber coherent state setting. That is not known in any of these other settings here, for instance, in the Bloch coherent spin state setting, or in any of these more general scenarios that you could imagine. Okay, so I think that there's really room there to explore this, to better understand what is really going on. And so I'll spend a few slides on that. And then I want to end really telling you something about the proof, because the proof is simple. I'm not saying that this proof generalizes to the general setting, but it's at least an understandable, rather simple proof that you might like. So here's the general setup. Right, so I want to bring this notion of coherent states under one roof. We have the Glauber ones, we have the Bloch ones. And so one way you can approach this is you look at a group G. Okay, and then you look at a representation of that group that acts on a certain Hilbert space H. Now, in that Hilbert space H, you fix a vector, unit vector. Okay. And then you move that, so this psi star, that's the corresponding rank 1 state, and you move that state around by your representation. Okay. Now that is somehow in disguise exactly what happens here. So there is one state, and the state is moved around by this representation of SU2. And here, oops. There is one state, namely the Gaussian, that is moved around by the Heisenberg. You might not see this immediately when I write it that way, but I'll talk about this. But this is really the general feature of the problems that we've seen so far. So fix a vector, fix a rank 1 state, if you want a Q state, you can also say that, move that state around using the representation. Now then, it's basic representation theory that you have the completeness relation. So the one that we verified sort of by hand in the Glauber case, and that I told you in the spin state case, that's verified with a certain constant C, which when it's finite, you can sort of include in the measure, which I mean, I showed you, which is the left and right. Okay, now the general question that I'm asking is, take a concave function f. Take it x log x if you want. And now compute the entropy of this, this is the classical entropy of this expectation value in the current states. And now ask for which rows is this infimum attained in a coherent state itself. That's the thing that we've observed. Right? That's what we've seen in the Glauber case, and that's what we've seen in the SU2 case. And I should say that it has also been verified for SU11. Okay, that's a non-compact group. And that's AX plus B, that's the affine linear group in one dimension. That's again a non-compact group, which is not so different from that. So for these 1, 2, 3 families, we have verified this. There are other few representation where it's also known, but that would be the general feature. And what I should say is that when we looked at these particular groups, there was always a natural choice of the psi star vector. You know, the psi star for the Glauber coherent states, that was the Gaussian, that's the ground state of the harmonic oscillator. Or for the Wehrl entropy, it was the ground state of, say, S3. Okay, so there was always, we took a special psi here. And so one part of this problem, it's a problem, it's not a conjecture or anything. One part of this problem is to understand the role of this vector psi star. So what sort of distinguishes the Gaussian there or the ground state of S3 or so? There is a representation theoretic notion of a highest weight vector. That might be relevant here in particular. Some people, including Gary Simon, have emphasized the importance of that in this. If you look at the book of Paranomov, then he uses has a different idea of what could be the relevant thing, but that's one of the math questions. So we want to understand if you have coherent states, when are coherent states better than others? I mean, so the coherent states, they depend on the psi star. Which are good coherent states and which are bad coherent states, so to speak. That's what we want to understand. And yeah. And I mean, it's not clear, I mean, whether we should look at this general concave function or just at the entropy. There is lots of room to play with these. Now let me just connect this. This is a very short slide. Let me connect this with what I said before, because you probably did not see the Heisenberg group and you did not see SU2 coming in there. So the point is, so the Heisenberg group has 3 parameters. I mean, it has the P and the Q, but it has a different parameter. And that's what you need to make, because translations and modulations, that's what you need here. So this is the translation, this is the modulation. They don't commute. So you add another parameter into the game, and then this becomes the Heisenberg group. But now this sort of additional parameter that just changes a phase, and that's not relevant for the problem because everything is anyway only defined up to the phase. And so therefore, really the coherent states, the way I wrote it here, parameterized by G, they really should be parameterized by a certain closed space where you mod out things that are irrelevant to the problem. It's a little bit also for in the SU2 case, you know, SU2 has 3 parameters, whereas the sphere has 2 parameters only. So there's a general algebraic way of writing this and get to a different space, which is sort of. So this, I mean, this sounds a little bit terrible when you look at this for the first time, but geometrically it's more natural. I mean, the phase space is 2-dimensional, the P and the Q, and you're also in a spin system, if you have a continuous spin system, then these vectors are S2 vectors, they're not SC2. So you really want to get rid of extra dimensions. I'm just saying this so that I don't, I mean, that you see that these 2 things, that my 2 examples really fit in this general. Okay, good. But now I think I'll tell you a little bit about this proof of this, this new proof of this generalized null conjecture. And so I remind you, we have this quantity. So rho is a quantum state on L2 R. We look at expectation values. We take a concave function from it and we want to minimize it. And as I already mentioned, we want to we can reduce ourselves immediately to the case of pure states. So rho, we assume that rho is psi. Okay, And the other thing, just because of scaling, I can choose H bar anything I like, and I do it so the formats become a little bit nicer. Good. Okay, so what do we have to do? We have to compute the overlap of psi with the coherent state PQ. And now, this is an identity, right? I mean, this is equal to something. So what do? I pull out a Gaussian. Now, so in P and Q, so that's a P squared plus Q squared. Then a phase, which is harmless, and then what's left over, I think of this as a function of a complex variable. Right? The complex variable is Q plus IP. And when you look at this formula, you see that this only Z enters in this formula and no Z bar. In other words, this is an analytic function. It's an analytic function on the whole complex. And then it's not good for us now to think about this F as really the variable. So this is an entire function which satisfies a certain integral condition, namely that's just a completeness relation that we had back there, written out in terms of this F function, right, where I put the Gaussian, I moved the Gaussian here, put the Gaussian back in, and so then this is just the original norm, which we can assume. So, and now I want to phrase this as something about complex analysis. I want to think of this as this entire function F, that's my variable. Okay, and in order to prove this, I will use 3 ingredients. And let me go through those 3 ingredients first. 2 of them are essentially obvious, and the third one is the one where you have to do. And then I'll tell you, after I've told you these 3 ingredients, I tell you how you can use the 3 things to cook up a proof. And then I'll tell you a little bit about the non-trivial ingredient and I mean how this changes when you look at other proofs. But let's, for the moment, let's just look at these 3 ingredients. Okay, here's the first one. You have 2 functions, h and w, on an interval. And you assume that your function w is an increasing function. And you want to optimize over the function h to make that integral, the product, as small as possible. If this is an increasing function, what will your measure be? Of course, it wants to be a delta at the initial point to make to pick up the smallest point of time. Okay, that would be the trivial answer. But now I'm making the problem harder by saying that this function, the function h that you're optimizing over, has to be increasing as well. Okay, so you cannot put a delta. I forbid you to put a delta at the starting point, because the delta is the most decreasing function you can imagine. Okay, so now you can imagine what does it mean that it's an increasing function. It means that you always have to push more mass to the right. But originally, you wanted to put all the mass to the left, so therefore it's not hard to imagine that the solution is to make the h constant. Right? I mean, that's the slowest you can make it increase. Okay, so that's exactly what this inequality says. This product, the integral of the product of these 2, is minimized when h is constant. This is the value, the average. I mean, h constant and has to be equal to its average. That's what this is. Now that's such a trivial argument that this was found by Chebyshev 150%. Okay, so that's the first ingredient. And it's easy to prove that. Now we go back to the analytic function. F is an analytic function, and now there's this U guy which contains this Gaussian factor. You know, I'm going a little bit back and forth. Sometimes I remove the Gaussian, sometimes I put it in. I mean, in some sense, this U is just the original overlap, right? I mean, that's the absolute value of the original overlap. And now I'm saying that this function, the maximum of this function U, I can bound by the integral of f. That's, well, perhaps when you see it at first sight, it might be a little bit surprising that you can bound a maximum by integral, because the integral is smoothed out. But then you should just think of Cauchy's integrals. Right? That gives you, if you have an analytic function, the value of one point can be recover from an integral. So just from an argument like this and a Cauchy-Schwarz inequality, you get to such a fact. And we know when we have equality in Cauchy-Schwarz, that's exactly when we this and that, and this tells you when we have equality. This will be give us the cases of equality in our proof. So in other words, I'm just saying this comes from Cauchy-Schwarz, the cases of equality. Now here comes the hard one. That's a little bit harder to digest, but let's think about this. So out of the function f, we've built the function u. And now we look at the super level set. So that's the measure of all points in the plane where this function u is greater than kappa. And now we measure this. How big? What's the size? What's the area of this set? And then we put a trivial factor in front minus 2 of kappa. And the assertion is that this thing, which is now a function of this level set where I'm cutting, that this is actually a monotone function. Okay. So believe me, we'll talk about this. I mean, here I could tell you that this is true, this was not hard. Here you have to think about it. Just, how you could arrive at this is take your cloud equivalent states, plug them in, and then you know what your UF is, that's a Gaussian, and then just compute this measure. And then you see that this function is a constant. Okay, so now the magic of the proof is sort of to say that this expression here, well, it's not constant anymore in general, but at least it's bound. That will come in exactly. Okay, but so let's believe these three things. Okay, these three ingredients. Now here's our problem again. Remember, UF, that was the Cassini function, lower symbol, short time Fourier transform, whatever. This is what we want to use. Now we write this thing in terms of its superlevel sets. That's a formula. No approximation, no nothing, no optimization. This is the function that we have. And so it's the derivative f prime that enters here, and here we have this quantity. And now at this quantity, we know that we can write it as this logarithm that we had on the previous slide, minus a non-decreasing function. Remember that's exactly the same. Turn it around, and this whole thing is non-decreasing, so the non-decreasing thing is what I keep. So this is a universal part, so this does not really enter the minimization problem. So in the minimization problem, I can replace this measure of the superlevel set simply by this non-decreasing function. And then you see already that this smells very much like you have a product of two non-decreasing functions, right? Because what does the fact that your f function was concave means that the derivative is whatever decreasing, right? So you see that this is relevant for the for this inequality of Chebyshev. Now, for the inequality of Chebyshev, we needed to know what, I mean, Chebyshev told us that the function wants to be constant. Okay, so, but we still want to know what that constant is. And that comes from the constraint. Remember that the state was normalized, so this was, I'm just applying this identity up here with f in the identity, and then I get a formula for the expression of h. So I know what the integral of f is. So therefore I can solve the problem, maximize this product, the integral of the product among non-decreasing functions with a given mean value. Chebyshev tells me what the answer is. That was the simple thing. Now, everything still depends on this value S naught. I didn't tell you what that was. S naught is this one here. That's the maximum value. Why is that so? Because right we have the function. Think of it as a Gaussian. Cut it, slices, and now of course when you reach the maximum of the function, then nothing is happening. Afterwards, the level set is 0. So that's what I call S naught. and therefore we don't know yet what this S0 is, so we do the whole argument for an arbitrary argument S0. We get a lower bound, and you know, then we have a lower bound that depends on this unknown value S0. So we just say, well, the worst case happens for the worst S0, but now we only need to look at this thing at the worst case S0, but this is an explicit object which we can work out, and then we see that this happens for S0 equal to 1. So, and then we go back. So we are actually in the, this thing is now 1, this is S0, this is 1, this is 1, so we have equality in Cauchy-Schwarz, so we got the cases. Okay, so that's the I don't want you to you know, see the details of this proof, but I want you to see the overall structure. And now let me jump a little bit ahead to the Bloch spin case. I want to tell you that proof now immediately, but show you what we need to change. Okay, so we have Bloch spin states. Before, we pulled out the exponential, and we had an entire function on the plane. And what do we do now? We pull out 1 plus z squared to the minus 2j. That's a fixed function that we pull out. And what have we left? We have left a polynomial of degree less or equal to 2j. You see, it's a very similar setup. And now, well, I mean, this is what you do. I mean, instead of so, you know, I use the stereographic coordinates, so instead of integrating with the sphere, I'm integrating over the plane, and have a certain geometry. That's nothing. But now the lemma that you have there looks exactly the same way. UF, that's the function that you have there, that's the overlap. And you look at its superlevel, the measure of its superlevel sets. When you compute the measure, you have to put this Jacobi factor in, but that's natural. Right? That's the measure of the superlevels. And you prove a monotonicity. Again, if you have the Bloch coherent states, then this function is constant. For general function, it's no longer constant, but it is not. Okay, so what I'm saying is the case of the Glauber coherent states and the Bloch coherent states, they just differ in sort of small details. It's a different function that you pull out. It's a different quantity for which you prove monotonicity. But apart from that, the general proof structure, you know, using Chebyshev, using Schwarz, and using monotonicity, that's still the same. Everything just is. So to conclude the talk, I spend perhaps some 5 minutes or so on that. I want to tell you a little bit on this monotonicity. And then afterwards, we conclude with some thoughts about what we have done. Okay. So let's remember, with UF, that's the overlap. The overlap between my state and the coherent states. And this is a function on classical phase space, which I write in complex notation, that's solution Z. And in the complex plane, I'm computing the measure of this. And I'm claiming that something is monotone. So what do I do? I take the derivatives. So, okay, I have my function, I cut it at some level, and I want to compute the measure of what's above. So I differentiate that, and now you see, I mean, how does this change when you change the height when you're cutting? I mean, that certainly depends on the set, the exact level set where the function is equal to kappa. But then, of course, somehow when you change now kappa, when you vary this cutting parameter slightly, it also changes on how steep the function is at these points, right? When the function is very steep, then that's how much it changes. So when you do the computation, this is the formula that I want to highlight. This is the derivative. How the measure changes when you change the cutting value. And so that's an integral over this curve where the function has this value. And then, as we said, it's weighed by a gradient of this function. Okay, good. Now you're sort of bothered by this 1 over gradient. Okay, because, well, what do you do with this? We don't really know what that is. So one way of getting rid of this term, or to dealing with this term, is sort of you Schwartz. So you take the geometric mean of here once the factor, the gradient factor is downstairs, once it's upstairs. Okay, so the geometric mean of these two things is where there is no factor at all. That's what we like. Because when there is no factor at all, then this is just the length of this curve. That's good. Okay, that's the length of where the function has this given value. Now, as was already hinted at, the length of this thing that bounds the super level set, so by the isoperimetric inequality, this thing, the length of the boundary squared, bounds the area. So we're in good on the right track. This area is the one we want to bound. This one, where the gradient is downstairs, that's the derivative of the quantity we want to bound, so that's good. So what have we done now? We've moved the gradient upstairs. So how do we deal with that? Okay, so gradient is upstairs. Now you look at this thing, and now what's a little annoying at first sight is that we have an absolute value of the gradient. But now think about it. You are on the super level set. That's where the function is bigger than that. So what is the normal to that set? That is given itself in terms of this gradient. So therefore you can get rid of the absolute value and write this just as the normal to the set, dot it into, now if you play through the math, you see that's a logarithm of the function. We know how to differentiate. It's nothing complicated. The logarithm gets the gradient upstairs and then the UF downstairs, but UF is kappa. So the UF downstairs, when you do the differentiation, that's okay, so that's a formula. And why am I happy with this formula? I'm happy because this is nu dotted into the gradient, so that's a normal derivative. Okay, so now I can apply the divergence, and I can, this is the outward flux, I can relate this to the divergence inside, and so what I get is the Laplacian of the logarithm of UF. Now, what was UF? UF is written up there, that's the overlap. But the overlap, remember, was of the form analytic function times Gaussian. So the logarithm is log of analytic plus a log of Gaussian is a quadratic. Good. So what is the Laplacian of the logarithm of an analytic function? Well, that is 0. That's the main thing, right? If the analytic function has a 0, then we get some balance. But if the analytic function is non-zero, we take the log of its absolute value, that has 0 Laplacian. So therefore we're left with computing the Laplacian of a quadratic. We can do that, that's a constant. Okay, and so therefore this, the bad term with the gradient was upstairs, actually turns out to be just another multiple of the value. And so now you see, here you have the area, I should say. Here you have the area, here you have the derivative of the area, here you have also multiple of the area. So everything is now in known quantities, and now you rewrite this, and you get this inequality, and that's the end of the proof. You might not have followed all the details, but what I'm telling you is that this is surprisingly general, because now if you do it in a Bloch coherence case, well, what do? You use the isoperimetric inequality of the sphere. Right? On the plane, we know that if we're given a parameter, then the optimizes it is. Now on the sphere, well, if you have a curve, once again, what is the optimal area? So what is the largest area? That's when you have a cap. Or when you do it in the SU11 case, then you look at the isoperimetric inequality on the hyperbolic space. Once again, you know it exactly, it's exactly these geodesic disks. And same proof, really literally, I mean, the point that I want to make is this is a very general approach. You just feed some isoperimetric inequality in, and then the right thing comes out. The magic here is a little bit that this logarithm of absolute value of analytic function is equal to 0, but that's what we had in the other problem as well. Remember, there was for the coherent spin states, F for the polynomials. So again, this thing disappears, and when you compute the corresponding Laplacian. Okay, so the feature that we like about this proof is that it deals with certain groups, namely Heisenberg group, SU2 and SU11, affine group in one go. So really everything is the same. Inequality is the isoperimetric inequality. I'm not sure, I have to say, and I want to be a little critical of this result, that this generalizes to different groups. So there's one case where Lieb and Soloway have been able to prove this corresponding Wehrl conjecture. This is when you look at symmetric representations of SUN. Okay, so right, so the problem has several parameters, right? So you have groups and you have representations. And ideally, we would like it to prove it for any group and for any representation. But what you also can do is you can look at certain representations, and some representations are nicer and more relevant than others. And one of these are the so-called symmetric representations, or anti-symmetric, that's the same thing, of the SUN groups. And for those, Lieb and Soloway were able to deduce the results. So again, minimal entropy states are coherent states. The proof that I presented does, at least as far as I know, not generalize to this setting, simply because you would now have to prove or use an isoperimetric inequality of the complex projective space, and there the isoperimetric sets are no longer the super level sets of the coherent states. So that's, I mean, I'm criticizing my own proof now. And nevertheless, I presented it to you because I still hope and think that it has potential. And I would hope that if somebody looks at this with fresh eyes, then you perhaps see something, and you see perhaps something about these analytic functions that help or that is unified. So just to summarize, for 3 different groups, it does work. It gave us new results, and in these cases of equality that have been conjectured and have not been known before. But really, the main part is still open. That means understanding this on a more general class of groups, understanding what makes these vectors or these coherent states that we use. I mean, everybody knows Glauber coherent states. Everybody knows Bloch coherent states. Why? What's so special about them? Except that we always learn about them. But we want to understand their optimality from this point of view of entropy. And with this question, I want to thank you for your attention.
Thank you, Rupert, for a very interesting talk. Other questions? Yes.
So first of all, I think one of the problems we don't understand the word analytic, right? I mean,
Okay.
That's often a problem. And then I have a very technical question: what happens if you put your f in your problem inside, so f of rho, and then measure that against the rotated coherent state?
Okay. Let me perhaps say a little bit about this analytic thing. So I think because there is a classical system in the background, you at least expect that the dimension is even. You know, you want to have as many momentum as position variables. So from that point of view, it's perhaps not so far to go towards analyticity or Kähler structure or whatever. I mean, that's just a very vague thing, but there seems to be some intrinsic well, symplectic structure. Let's put it like that. Which is used here, but which we are not able to use in some other. I mean, right in the symmetric representations, we do have a complex structure. Again, yeah, it's analytic functions in several variables, but we don't know how to use it. Now, for the other question, I have to say I have not thought about it. Wait, right. We do it, we put it in. It's, yeah, an interesting question. I mean, it's be nice if we would all explore that. Thank you.
Are there any other questions? Yeah.
Yes. I'm not sure. So I ignored, right? I mean, I ignored in this talk several questions about, you know, convergence and integrability. So really, there should be always statements. I mean, that quantities are finite, and right. I mean, some things can be infinite. You're right. I ignored some things. This becomes particularly relevant when you look in this hyperbolic framework on this affine group, because then there are representations that are not square integrable. And I mean, then I left those out because I did not want to get into this thing. But there, this really becomes relevant, and one needs to be careful about that. Thank you.
You said that these Wehrl entropy is an upper bound on the
yes.
One can one construct suitable lower bound in terms of the
So I think the answer to that is no. So I think the difference between the two things can be arbitrarily large, I think. But one might do something under additional constraints where you avoid some particularly bad situations. Yes, I mean, it's a natural question, but I think so the naive, the first try that you would do, that does not work. Or so at least for the difference. I don't know about how you can put constants in, but the difference is not bound in the other. Okay. Yep.
there is the so-called minimum output conjecture of the Russian.
Yes.
And the optimizers are the Boolean states.
Yes.
And I wanted to know if this framework is related to this program, and if these results like implies.
So the short answer is I don't know. The bit more in more detail is, so when De Palma proved this, so he looked at the Wehrl entropy, minimizing the Wehrl entropy under a given entropy, given phenomenon entropy. Then he used these Gaussian channels and used monotonicity property of those, and that we know that Gaussian states are optimizers for those. And he used all this property, all this technology that was developed in that setting to prove that. So it sounds very much like there is a connection to that. Although I don't know what it is, and in particular, I know even less what the analog of that would be on the sphere, with the spin. You know, what would play there, the analog of Gaussian states, and would one have their similar theorems? So I'm coming from the other direction, and I want to take this as a starting point, and then perhaps also understand better these systems on the sphere, using analogies to all these things we know about Gaussian channels.
Is it easy to explain what you have to add to the proof to get the stability result, or do you have to do something completely different?
It's okay. So there is a relatively easy proof of the stability result when you settle for a bad exponent. I mean, for an exponent less than 2. So I think, is it 3 or 4? Somehow this one gets there with relatively minor modifications. To really get to the optimal exponent 2, you have to work quite a bit harder. And to be fair, I should say that this was in a different problem, was accomplished by Gomez, Guerra, Ramos, and Tilly. And what we did sort of was taking their results, playing a little bit along with it. So they had gotten the power to the optimum. And we could, in a different problem, and we could carry this power over to our problem. And that's really, and it's very long, and if I'm saying that they go on for 20 pages or so and do lots and lots of counts. And it's the same strategy. I mean, you look at this monotonicity property and then you try to understand better that on long enough stretches, you almost have to reduce it. That's roughly speaking what you want to do. But it's complicated.
Are there any further questions? If not, let's thank Rupert again.